Colleen Dwyer.
I'm Liz Olson.
And I'm Jessie Butler.
And our project is on
Projectile motion. I thought we were doing that all together. Okay. Okay, so for this project, we're going to all work together on throwing things and doing various activities that will demonstrate what projectile motion really is. And Jessie, would you like to add anything?
Well, we've had a lot of fun with this video, so we hope you guys will too.
Wait for them a little. Okay, yeah, that's good.
Yeah, go.
Girls, would you like a snack?
Yes, please.
Totally.
Projectile motion.
We thought we would start off with the dictionary definition of projectile motion. Projectile motion refers to the motion of an object projected into the air at an angle. Some examples include a soccer ball being kicked or someone jumping out of a plane. So we thought we would give you some everyday examples of projectile motion. One example is a water balloon fight.
One is also dropping a salt shaker.
Another one is jumping off the diving board.
One is throwing a baseball.
Another one is dropping your pencil in class.
Throwing a piece of paper.
Another one is shooting a marker into a marker bin.
What the heck? How did you think of that?
Like Mr. Kavanaugh does a lot.
Another one is throwing a paper towel into the trash can and missing.
As you can tell, projectile motion is used in everyday life. So in this video, you will see a couple of examples that we've come up with. So for our project, we are going to roll 6 different sized cans off the coffee table and measure their projectile motion,
The biggest one is at least 10 times bigger than the smallest one.
following the rule of 10.
I will be documenting the points, the grams on each can, and the centimeters, how far they go with each weight, and an X and Y value. And then we'll graph them.
And we'll find the slope of our graph by calculating it on our calculator after we plot the points.
And that will be our mathematical model.
Yay!
Enjoy!
For this project, our independent variables are wind, the can, the weight of the can, and our dependent variables are gravity, the friction on the table, and yeah, that's it. Our controls for this project are the distance from the coffee table to the ground and the placement of the can on the coffee table from where it falls off of the coffee table.
My prediction is that when these cans are pushed off the side of my coffee table, that they will all land in about the same place. My hope is that they do not dent my floor. Okay?
So we will be recording the distance a can falls to the floor. We are using our Super Kids ruler because we are all super kids. So we start it from here. So we take the can. This one weighs 113 grams. Every single time we will start it at the edge of the coffee table and let it roll and record. Colleen will record where it hits and Liz will write down the numbers. So 113 grams is at 7.5 centimeters. Whoa. The next can is 283 grams. We started at the edge of the coffee table and it hit at 10.7 centimeters.
Next can.
The next can, 298 grams, start at the edge of the coffee table. And it hit at 11 centimeters. The next can, 454 grams. Start at the edge. It hit at 12.5 centimeters. The next can, 538 grams, hits at 13 centimeters. And our final can,
Whoa.
which is 1.08 kilograms, which is 108 grams.
Yeah. No,
No,
it's 1,080.
1,080 grams. 108. Okay, ready? Whew. Hit at 17 centimeters.
So now we're going to find our mathematical model by plugging in all of these data points on our calculator.
Well, like any great scientist, I now know that my hypothesis was incorrect. They did, in fact, not all land in the same spot. I'm hoping, still, that my floor is not dented, but at least I have a rug.
So what I'm going to do now is draw a motion map of the cans, of each can falling down. But I'm only going to do one motion map because they all do the same general motion off of the coffee table. So I'm going to start, and I'm going to draw the carpet on the ground, like so. It's just going to be a horizontal line from my paper. And I'm going to draw the coffee table right here, like that. And here is each can. So I'm going to draw a dot for the can, like so. And I'm going to draw a horizontal arrow, like that, to show that the motion is going off of the side in a horizontal way. And then I'm going to do another dot for the can's motion directly below that arrow. And I'm going to do a vertical arrow down, a small vertical arrow, because that's going to show the acceleration down towards the ground due to gravity. And then I'm going to draw another circle right below that arrow to show that, just show the distance that the can has traveled at this point. And each time, these arrows are going to be the same distance. But the vertical arrows are going to be more dramatic.
Why is that?
Because each time it falls further down to the ground. So I'm going to do one last one. And it doesn't matter if the arrow goes past the carpet because it shows how big the motion is. The carpet just stops the motion when it falls on the ground. And so here is your motion map.
Physics is so fun.
That's how it looks like. Cool.
That probably took up all the rest of your time.
So our data appears to be a linear regression where centimeters are directly proportional to grams.
So we graphed it, and it appears to be a linear graph, and we found our mathematical model.
And our mathematical model is linear, so we did centimeters for the y, and then we did the x of grams multiplied by 0.009 centimeters, which would actually be 0.9 millimeters. And that means that there are 0.9 centimeters per gram applied to each can. Oh, and there's no b to this equation because if there would be no grams falling off of this table, it would not travel any centimeters. So that's the end of our project.
We hope you enjoyed. We had a pretty good time with this.
Yeah. And so
Merry Christmas!
Merry Christmas.